Welcome everyone, hope you're all doing well. Today I'm going to be making a video discussing the homework related with chapter section 8.4, intersections of lines in 2 and 3 space. Let's begin. We're going to need a bit of background first on how these problems go. So let's first understand the geometry of how two lines can look like in 3 dimensions. So this is a really good illustration in the book. So there's 4 possibilities for how 2 lines can look in 3 space. I labeled them in cases, so there's case 1, case 2, case 3, and case 4. In case 1, we have one intersection point. Case 2, the lines lie directly on top of each other. We call that coincident. In case 3, the lines are parallel, and there's no intersection. And in case 4, you can think of it as one line lying on top of another, but because we're in 3 dimensions, these lines will never intersect. This is referred to as being skew. We can even classify these 4 cases into 2 types. That's how I labeled them. I call them type 1 and type 2. So type 1 are the cases where they're non-parallel direction vectors. That would be the case for case 1 and case 4. Our type 2 classification would be where the direction vectors are parallel. This is in case 2, where the lines are coincident, and in case 3, where they're parallel and distinct lines. Okay, that's good. All of these problems also have a quite general procedure that you can go through. So I outlined that here as well. In step 1, we determine the line intersection problem type. So we're just determining if it's type 1 or type 2, non-parallel or parallel direction vectors. Step 2 entails writing the lines in parametric form. Step 3 involves equating the like coordinates when written in parametric form. Step 4, now we have 3 equations and 2 unknowns. So what we can do is choose 2 equations out of the 3 to solve for t and s, or the usual parameters you'll see, and we're going to solve for t and s using elimination. So I wrote a note here, but as to why we're only picking 2 equations, because to use the elimination process, remember, we need the number of variables to equal the number of equations, so we want 2 equations, 2 unknowns. Okay, then we have a little separation here into whether now the process can change if you have a type 1 case or a type 2 case. So for type 1 cases, we examine S and T in the non-chosen equation out of the 3 to verify if we have one solution or the lines are skew. And then if there's a point of intersection, we can plug either S or T into the respective line 1 or line 2. That's step 6. We can divert here into type 2 problems where this is what you'll see. If you get a mathematically true statement from the elimination process, so 0 equals 0, that indicates the lines are coincident. If you get a mathematically false statement, like 5 equals 0 or 6 equals 0, which we know is false, that'll indicate the lines are parallel and distinct. Okay? So you can complete all these problems under the guise of elimination, but there is a note that I want to take over. I'm going to show you guys. In the case of type 2 problems, so when we have parallel direction vectors, this entire procedure could be ignored, and we simply check if one of the points, typically you'll use the position vector, on one line is a point on the other line. The reason this works is because we've already separated it into 2 classification types, type 1 and type 2. If the lines are coincident, then all points must be the same on each line, meaning if a single point is not on that line, it has to be the other case, which is they're parallel and distinct. That's the logical reasoning you use for this this other procedure, if they're of type 2 problems. Okay, so let's get into it now. So here we're solving questions 4A and C, and it's asking us to determine if the parallel lines in each pair are distinct or coincident. These are all type 2 problems because, as you can see, each of the direction vectors for each line are scalar multiples of another. In this case, times 1, the first direction vector gets the other one. And for this case, if you times by -1, you get the other direction vector for line 2. If you times here by -2, you get the second direction vector. And I don't exactly know what scalar multiple it would be in D, but I can assure you that there is one. I guess, yeah. All right, so we're doing problems A and C. So again, I'm following my procedure. The procedure only diverts after step 5. So we continue as usual. So find the parametric equations of A. I did that right here. Then I equate like coordinates right here. Okay. Now here's where I do something a bit different as compared to what you've probably seen in class. But I like to move everything over to one side, and actually I like 0 on my right-hand side. So that way I can see all the coefficients in front of S lined up nicely. I can see all the coefficients in front of T lined up. And I can just see just pure numbers as well. This is my preferred way to do elimination. And this is also, when you learn about matrices, this is kind of how it's done in matrix form as well. Okay. I will label usually the two equations I'm doing elimination with. I'll just label them 1 and 2. I don't really care about my third one. I'll label it if I have to in the problem later on. So I'm going to be working with these two, this one and this one. And my choice came from the fact that every time I see a coefficient of 1 in front of something, I know it's easily I can use some algebraic manipulation to get it to a coefficient I want it eliminated against. So in this case, I did 1 times -7, and I added it with equation 2, and you can see this addition here. Okay. Once this elimination process was done, though, I got a mathematically false statement. So now I've realized this is a type 2 problem, so I had to go down this following tree. And then I realized I got a mathematically false statement. 8 does not equal 0, obviously. I wrote contradiction. So then that means these are parallel and distinct lines. Okay? Other forms of this you can see is something like this, 0x equals 5. As you can note that no x out of all the real numbers would work for the above equation, because any x you give it, the equation on the left-hand side will always be 0. And we have on the right-hand side a 5. Okay, part C. Same deal. I wrote the parametrics down here. I then equated like coordinates, x's with x's, y's with y's, and z's with z's. And then I moved everything over to the left-hand side, making the right-hand side equal 0 for each equation, where I usually like to line it up in alphabetical order. So I put the s's first, and then I followed it with the t's. Okay, so same deal. Now, I chose the two equations I'm going to do elimination with, 1 and 2 here. And then I realized that I have an s, and I can add it with a negative s to get rid of s. So when I do that, I end up with a mathematically true statement. 0 obviously does equal 0. Therefore, these lines are coincident lines. Okay, so that's it. Another example of a mathematically always true statement would be something like 0s equals 0. I just replaced x with s in this case. But any s I plug in from the real numbers will always work because it's multiplied by 0 on the left-hand side, and I have on the right-hand side a 0. So 0 obviously will equal 0. Okay, for A and C done. Notice though, the key note here is that I realized these are all type 2 questions, so I kind of already expected a result I was going to get. Okay, moving on. Question 5. Here I'm doing actually 3 questions, so this is a bit different from the homework you're given. You're only expected to do 5A and C. I'm doing 5A, C, and D for you guys. Okay, so first what I did, I looked at each problem and I recognized whether it's type 1 or type 2 I'm working with. So here, in part A, I'm working with a type 1 problem. No scalar multiple will give me the other line's direction vector. C is a type 2 problem, as I can just multiply by 1 to get the other direction vector. And then D is also of type 1 because there's no scalar multiple that can multiply my direction vector of line 1 by to get the direction vector of line 2. So, yeah. Okay. This makes my problem already a lot easier. So now we start with 5A. Wrote down my parametrics as usual for lines 1 and 2 right here. Equate the like coordinates of x, y, and z. Move everything over to the left-hand side, make the right-hand side equal 0, with the s's first, followed by the t's, and then just the numbers. I'm always going to prefer to do elimination with 1 and 2, the equations I labeled 1 and 2. So here, I did 1 plus 2, and then I got rid of the s's again. It seems like I have a preference for getting rid of s's in a lot of these problems. But you could also do t's, it doesn't really matter. So then I added the 2 equations. And then I got minus 3t equals 0. So then I got t equals 0. Now remember, I was working with a type 1 problem. So I'm going now down this route. Okay? So I'm not expecting just a mathematical statement at the end. I'm actually going to get something for t and s. So I got t equals 0. Now I'm just following the elimination process. I could either sub this into equation 1 or 2. I specifically chose to sub it into equation 2 here. And then I've solved for s, which was negative 5. Okay, so I got s is equal to negative 5 and t is equal to 0. The final part is the equation that I did not check, the equation that I did not use for the elimination process, which I here labeled 3. So I did not use this equation at all during the elimination process. I'm going to check my s and t values into that equation. And then when I do that, I get negative 12 equals 0. I wrote not equals, obviously, but the equal sign should just be equals. So this is a mathematically false statement, and we knew it was of type 1, meaning the lines had to be skew. These are skew lines. Okay? If you got a mathematically correct statement, we know there's a point of intersection, and we're dealing with case 1. Okay, so these lines are skewed, 5A. 5C, okay, same deal. Well, actually, not really. First, remember, this is a type 2 problem. The direction vectors are parallel here. So write the parametrics down for each line. Boom. Next, equate them. Good. Then take everything over to the left-hand side. Right-hand side equals 0. Okay, good. I labeled 1 and 2 for what I'm going to do elimination with. And I got a statement at the end, which is 0 equals 0. This is clearly a mathematically true statement, and it's a type 2 problem, meaning the lines are coincident. Okay? I just wrote therefore coincident, but I guess I could write coincident lines. Okay. Part D, the problem here is not going to just end with a mathematical statement. I'm going to get values for S and T because it's a type 1 problem. So write the parametrics. This always stays the same. Equate like coordinates. Okay. Now notice here though, this problem is quite peculiar because you actually don't even have to do the whole elimination process in a sense, where you can just find t quickly in equation 2, which I labeled here. That's what I did here, solve for t in 2. And then I plugged it into 1, okay, because that's where I need to find s. So it's still technically elimination because I'm choosing 2 equations, okay? But I am forced to choose 1 because obviously there's no s value in 2. So then I got s is equal to negative 13 over 6. But now I have to check my result in equation 3, which I did here. But at the end of the day, left-hand side does not equal right-hand side once I plug in my s and t values, meaning therefore the lines are skewed because this was a type 1 problem to begin with. Okay, that's good. Moving on to question 6 now. So here I'll be doing A and C. So both of these problems are of type 1 again, because there's no scalar multiple that I can multiply the first line's direction vector by to get the second direction vector. So they're both of type 1, meaning I'm going to see some values for s and t and not just some mathematically true or false statements at the end. So write the parametrics like so. Equate like coordinates like so. Move everything over to the left-hand side. Right-hand side equals 0. Now choose equations 1 and 2, which you're going to do elimination with. I chose these two here. And I could just add them to get rid of the s. Okay. I solve for t, right here. Once solving for t, I sub that into equation 2. I could have easily as well chosen equation 1. I chose 2 because I don't really know. The substitution might have looked simpler to me then. Okay, so I got t. I can now solve for s in equation 2. So boom, I have now both parameters, t and s. And now I check them in 3 because this is a type 1 problem. I'm trying to drill that into your head. And having the classification down early on is so important. Okay, plug t and s in. 1/2 plus 1/2 plus 4 equals 0. 5 does obviously not equal 0, so therefore the lines are askew. I get a mathematically false statement at the end. Okay, moving on to 6c. Same deal. Write the parametrics of each line. Equate like coordinates right here. Okay. Move everything over to the left-hand side. Right-hand side equals 0. Choose equations 1 and 2 to do elimination with, right here and right here. That's the ones I chose because I could just take equation 1, multiply it by 5, and add it to 2. Okay. And then that gets rid of s, that gets rid of t, and that also gets rid of plus 5 minus 5. Huh. That's quite strange. I did not expect a result to give me just a statement like that at the end. It was a type 1 problem, right? So you might be wondering, what is going on here? Well, if you think I messed up, I kind of did. So I wrote a word of caution here, which you should understand quite well. Equations 1 and 2, the ones I initially chose, are the same up to multiplication by a scalar. Multiplying equation 1 by 5 will give me equation 2. So they're not unique in that sense, up to scalar multiplication. This does not mean the lines are coincident, because I determined that by classifying type. That's why classifying type is so important. But that our choice of equations to perform elimination on is not appropriate. So I cannot choose 1 and 2 to do elimination with. This technically would be, it's not adequate enough to give us the correct information. So I'm forced to choose equation 3 to do elimination with. 1 and 3. Okay, not the problem doesn't change as much, right? I just multiply equation 1 by -2 and then add it to 3. All right. I find S. I eliminate S. I find T here. Now I can sub it into either 1 or 3. I chose to sub it into 1. It was just simpler. So now I have a value for T. I have a value for T and a value for S. Okay. Now we check it in equation 2, the one that was not used during the elimination process. Okay. And then when I plug that in, I get left-hand side does equal right-hand side, 0 equals 0. So that means we were a type 1 problem. The check was fruitful in that it showed us that left-hand side does equal right-hand side for the equation we did not use in the elimination process, meaning there is a point of intersection. Okay, now we have to actually find that point though. So now we bear the fruits of our labor. You can either take T or the S value and then plug it into the respective equations. I chose S because I like the value 0 is always easy to plug in. So that means if I chose S though, I have to plug it in to line 1 right here because that's the line that has the parameter S. Okay? So I chose S equals 0. I could have chose T equals 1, but then I had to plug it into the other line. Doesn't really matter. For line 1, plug in S equals 0. When I plug that in, I get the vector 2, 4, 2. Remember, this is a vector equation, but in our application, that means the lines actually intersect at the point 2, 4, 2. Okay, good. That might have been a mouthful, this question. This chapter section is not so difficult. It's just doing enough problems will get you familiar with certain things you might see, and therefore you won't be afraid during a test situation. You'll have seen everything. Okay, good. Thanks for watching, everyone. This is my final video. I'll help you review at any time I'm available. Thanks to all of you guys for watching. Thanks to Ms. Kranik. Thanks to my friends as well for actually editing and reviewing my stuff sometimes as well, making sure my algebra wasn't off too much. So, yeah, I'll see you all in class, but thank you. Have a great day.